stuff, so maybe we can move forward and you can see the continuity of where we're doing. We are going to discuss about anti-atherogenics, and we're going to also discuss about a new concept that we are going to introduce, which is the cellnet. We will see what is that, but later on. And finally, we are going to talk briefly about the possibility that we will offer this membership inside regeneratics. Next. Okay, I made a PhD in aerospace engineering, but it would point out things. So maybe we can do it with this. Oh, thank you very much. Applause to I'm more comfortable right now. So the good point is that we have some trajectory, and I would like to know why I think it's solid. I am very honored to say that we made work in anti-regenerative that may border on different complexities of different kind of anti-regenerative. For example, angiogenesis, which is different for the oncoangiogenesis, but also lymphoangiogenesis, arteriogenesis, or vasculogenesis, and all. There are different kinds and different kind of treatments. It's different whether it is that anti-atherogenics or is, for example, pulmonary hypertension. But the good point, I'm very honored to say that someone with more than 65,000 Google Scholar citations made work very similar, and I am very honored to say that it's someone with very high reputation, like did that and put his name on that. Means that maybe and just maybe we are doing things in the proper direction. And another previous one that I want to say is that by 2020, SARS-CoV-2, there were some findings about the microangiopathy, and we could see that in 2022 there was integrated connections between the coronary microvascular disease, which is one of the main key problems with angina pectoris symptoms in long-COVID patients, which is a kind of chronic disease after the pandemic. And by that time, there was a main concept about dysautonomia. But I was very fortunate that in the Cardiovascular Institute of Spain, someone who is, for me, is very wise man, both professionally and intellectually, Scanner, decided to listen to that. And 2 years later, they found the evidence. I presented to someone who found some evidence to that, and they received the Gran Club de Comunidad de Madrid, Isabel Díaz de Leso were awarded with that. So maybe and just maybe we have an interesting line for the future. Well, I founded, so that gave me the confidence for founding regeneratics, which means bioinformatics and regeneration, regenerative bioinformatics. And there are, in that future line, we have a main goal, which is anti-regenerative and immunoregenerative, which means the regeneration of blood vessels, but not only blood, but also lymph and immunoregeneration. We plan and open a hospital by mid-27 and 28 for cell reprogramming therapy. We have interesting discussions in Dubai, but also here in Spain with different actors. And the long goal, of course, is going to be, let's say, clinical regeneration, but you know what I mean. So I think that's the strategy. But maybe just maybe we are not interested in direct investors. I'm going to explain politely why. Because if the company, I'm fully compromised with the company. I have personally, it's a personal project, and I want to give the maximum quality. I have some affections after the pandemic, and I am 100% sure that I want high quality outputs of it. So maybe direct investors could expect after multiplying by 4 the value of the company to make a sell-off, and maybe it's not interesting for the long term. But I do interest in membership program and in science projects that are highly profitable and could inject capital into the regeneratives So, of course, the direct investors are very welcome for the size project to carry into. And well, 2025 has been a great year. We have one gold medal in mathematics in the computational team, mathematics of Spain, and other medal in biochemics. We have our own. In a few minutes, we will have the pleasure of having a short conversation with him. And why anti-atherogenics matters? Well, vascular inflammation is the major senescent, not the major, but let's see that is one of the major senescent drivers. And we will see that. The vasculature also is the fastest in aging. And well, there's a kind of, not a kind of, there is some feedback between high hypertension and low-grade systemic inflammation, and of course cardiovascular ILS2025 is called first cause of death, for example. So atherogenics is a kind of typical bond. So I think that's interesting. It's not me who is saying this. They are very recent journals. You can see here that in the vascular system, the xenoproteins basically mid-age onwards triples the xenoproteins with the rest of organs. And there is also a turbosenescence of the vascular system if you have continuous several infections of SARS-CoV-2. So even if you feel asymptomatic of SARS-CoV-2, the aging clock, vascular aging clock is another thing, and it's top journals to say that this is very recent. There is no magic pill for this. So cellular crosstalk is important, but also a new concept that I think is also important, which is cellnet. It's a kind of game with the words with internet, but what is cellnet? Cellnet is actually, there is a kind of neural network, but chemically driven with all cells. It's not just cellular crosstalk, but it's a huge coordination, and this is very important, for example, for gastrulation, or for example, for major vasculomorphogenesis, which is the major kind of, there are many kind of agile regenerative, this is one of them. But just to see the complexity of the problem, consider that you inject eight anti-inflammatory agents, and if you, with the same anti-inflammatory agents, you change the distribution, you obtain completely different results for the markers. This is actually for human umbilical vascular cells, which is very common for experimentation. It's a kind of, it's very complex, but it's a kind of problem that you have to engage, which is the right combination of a safe box, of a ball. Which is the right combination, because there are a lot of combinations. Well, I think that maybe regeneratics is doing a good job in guessing in the minimal number of iterations, in the minimal number of experiments, which is the solution that you have. And maybe it could be useful with this small contribution to other companies that want to make less experiments to find the same, to find the goal treatment that they would require. So, to give a particular, very simplistic scenario of what I'm doing, consider, for example, these cytokines, pro-inflammatory, to drive the cell into an initial inflammatory state, and then we are trying to recover the initial state with different anti-inflammatory vector. Of course, we have some markers to see how the things are going on. And the point is that after the initial inflammation, we are able to analyze the complexity of the problem. And after that, maybe you have to make a principal component analysis or another filter algorithm techniques, but eventually you perform machine learning, and in only 2 iterations, you have the 2%, only 2% of the initial inflammation, which is a clinical zero inflammation. So, of course, there are many study limitations. I'm not completely happy with that, because we have to test that into, we have to test it. We have to test it in vivo. This is just in silico. So it's fine, but we need experimental validation always. And the good point is that we have enough data. We were able to do a deep learning to predict the series made by Lucas, which is here. I'm very happy with my team, by the way. And it's great that we are very lucky to have here Dr. Pichardo. Be very welcome in Israel. It's a pleasure to have you here, the Chief Scientific Officer of ILS2025, and also made a postdoc with Davis. Thank you very much. We are very lucky because we can do the experiment that we require. We have interesting collaborators.
And we decided to partner with regeneratics and the process team because we are very interested in modeling not only the secretomics, which we are very interested in, which is a tool that we want to use in order to improve and extend health span in people.
This is something that connects with the last part. I think it's very interesting because we take into account in our models that something that we knew intuitively, that is the cells are able to adapt and to react. And how is that possible? Because very probably there were a kind of machine learning inside the cell, intracellular. And those evidences have been recently published. This is in September, 1 month ago. 1 month ago, they were able to store 100 bits of information and perform machine learning with the molecules directly intracellular. So this is machine learning proteomics driven, and it has been published in Nature and Nature Biomedical Engineering. And this is key because it aligns with our last model. Actually, we released something. I'm going to make a kind of a spoiler on the next slide. But we tried to make a huge study because we were able to control the proteomics and the transcriptomics at a cell level. Well, not to control, but a small stage of controlling. Okay, maybe it's more honest to say that. But we were an epic fail. Okay, as we say in the normal convention. When we try to simulate the anti-atherogenics process at the myocardial level, so intracoronary and microvascular bed around the intracoronary, we failed, and we wonder why we failed. And maybe when we attended to the traditional convolution model that is in the normal artificial intelligence of as industrial secret more things, but we find out that probably it's because there are no true convolution in time. The cells make that kind of artificial intelligence. It's not artificial, it's bio-IA. And they are able to do that, but they interact in the real time. So molecules are not going to flip in each iteration. Numerically, when you do an iteration, the numbers flip. There is a glitch in numbers, but the cells don't do that. They remember everything, and mathematically, that's a convolution, a true convolution network. So we made a new kind of true convolution neural network that I call it TrueCo, because TrueCo in Spanish means trick. So TrueCo, and with this new model, we were finally able to control inflammation at the cellnet. Not only cell therapy, but cellnet therapy. Now, okay, now so the point is that, it's a pity. But this is a real-time conversation of the cells. It's a pity because I should have expanded. There is ripples, small ripples in the waves, and this is a real-time talking simulation between many kind of cells. And the first window is proteomics. The second window is transcriptomics, which is slow. Oh, 1 minute. Okay. And then we have stabilization of the signaling pathways and finally the markers. And this is the result. We were able to control the inflammation. The red is bad, green is not anti-inflammation, but at least control the inflammation in the myocardium. Thank you very much for your attention. I want respectfully in the three languages say goodbye also. So, Felicio Ancaise in the Kaishu, y gracias, muchísimas gracias por su atención.